In this experiment, Newton's second law and the effects of a multitude of forces will be observed by dropping an object and following its motion. Concepts of this lab will of course include Newton's second law as well as weight force, gravity, and drag force. Though these seem like simple principles, they can drastically change motion of an object. In this experiment, I exemplified gravity and weight force by dropping a tennis ball from rest at a determined height. We used Tracker to trace the motion of the falling ball. The clip of the experiment is seen here. As you can see, the tennis ball does not have constant motion as seen in the graph to the right. Gravity was the only force acting upon this ball as it pulled on the weight of the ball. Gravity holds an acceleration of 9.8 meters per second squared, and as you saw in the tracker clip, that is why the graph didn't hold a constant slope, signifying constant velocity. We now continue to analyze the motion by creating a computational model using Python. Utilizing this template of the code and adding in details such as the mass of the ball, initial position and velocity, and most importantly, the gravity, the code becomes a replication of what happened in Tracker. Using the total time from the release of the tennis ball to when it hits the ground here, and applying Newton's second laws in the code here, we construct the computational model. The difference in this lab is how we take into account the weight force and gravity, as seen here. The net force is the effect of gravity pulling the ball down. Now, when we run this code, we see how that the motion looks right visually. When we compare the graph of the computational model to the data taken from Tracker, we see a very noticeable discrepancy in the two sets of data. This is due to the fact that we did not take into account drag force in the computational model, another very important aspect that cannot be ignored. Going back to the code, we modify the lines a bit by adding in the presence of drag force, as seen here. We specifically use a turbulent drag force. Turbulent drag force is calculated by multiplying a constant to the magnitude of velocity squared, and is a flow of the air that pushes against around the ball when it is dropped. The problem lies in finding the constant as it changes based on the size, shape, or texture of the dropped object. We estimate this constant by trial and error of finding the closest value that will give our ending position. Our ending position was negative 2.171 meters at the end of 0.586 seconds. Now, when we run this code once more, we find a difference in the motion of a very slight bit. And as seen here, this is a very approximate value to our ending position, showing that the constant was an accurate estimate. As you can see, when the drag force is included, the lines representing motion better match up with each other as presented by the blue and red lines. The lines still, however, are not an exact match, and that can be due to the human error of tracing a blurry ball manually on Tracker, or imperfect camera angles on the clip. However, it is definite that the new line of data expresses the motion much better. Finally, we conclude this lab by asking a few questions. Questions we ask ourselves are: which model best predicts terminal velocity? The computational model with drag force best predicts terminal velocity because at some point, the drag force will equal the driving force pulling the ball down. Any other model will not sufficiently predict terminal velocity as there will be no other force that will counteract gravity itself. The final question we ask is: what if the object was initially thrown downward? Would this change anything? The answer is no, the terminal velocity would not be affected by this. When we write an initial velocity for the code and we rerun it, we find that though the velocity still starts off parabolically, the line begins to linearize itself, showcasing the beginning of a constant velocity or terminal velocity, answering this question visually. Only the final distance traveled under the same time constraint would change. And that is the end of this lab.